Welcome back students to another video of online classroom. In this video we are going to discuss about stresses in Anchorage zone in case of prestressed concrete. So before we go into the discussion, uh, let me first clear it out to you what is basically an anchor or anchorage zone. As you already know, in case of post-tension concrete, first the precast member is casted with some hollow tubes or some profiling done beforehand, and after that through those tubes you pass through the tendons and ultimately tensioning it, and then after you tension the tendons you anchor the or clamp the tendon wires with something called anchor and connect it to the sides of the precast member or the end of the precast member. So that particular end on both the sides of the precast member is called anchorage zone, where the tendons are clamped to the sides of the beam. Alright. So since we are doing a pre-stress post-tension beam, obviously it will be carrying, the tendons will be carrying some pre-stressing force. So if you think clearly, you'll surely understand that the anchorage zone or the anchor or the clamp is actually passing the whole load to the beam or the pre-stressing force to the beam through this anchorage zone only. So that huge amount of load is passing through a small area where the tendons are clamped. So in order to make sure that the beam does not fail in such huge stresses in the anchorage zone, first we need to know uh, how much stresses are developing, and accordingly we need to design the anchorage zone to make sure that it does not fail in shear, moment, tension, whichever may be the case. And obviously we'll be discussing all of that in this video. All right, so let's get started. As I mentioned earlier, see, this is a typical prestressed precast member which has been post tensioned. All right, let's use this example. So this is a typical post-tension member which has been precast prestressed member which has been post-tensioned, and there you have a anchorage plate or clamp which is connected to the end of the prestressed beam, and which is supposed to keep the tendons clamped at this anchorage zone. So first what you do, you have tendons through this beam. You first provide apply tensioning to that tendon, and then clamp that uh, anchorage plate with the tendons at the end of the beam. So obviously the tendons will be applying forces on the anchorage plate, and consecutively the anchorage plate will be applying compressive force to this particular end of the section. Now we usually assume the pre-stressing force is taken by overall section, right? If you remember, the direct stresses we used to calculate is P by A. A is the cross sectional area of the whole section, that is B into D. But in this case, if you see, that whole force is basically passing through anchorage plate which is having one particular dimension of 2 yp0 or ypo. Alright, So obviously there is going to be huge amount of stress that is coming here, right? And that will create a lot of loading conditions, mechanism happening in the section. All right, but we are basically concerned about one simple thing here, is that whether this anchorage zone will cause any tension within the beam or not, because we already know concrete is weak in strength, so we need to make sure that no tension occurs within the beam. See, if you see these diagrams, this diagram, I'll just reiterate, these diagrams are not of a tendon. This diagram basically show the loading profile. Like if this anchorage plate is having a huge compressive force on the beam, how does the compressive force transmit within the beam? These arrows represent that loading flow. All right. So if you see, if my loading flow is like this, if you if you see, then in that case, say we are having a profile, we take a membrane in the neutral axis or the center of this particular anchorage plate. You see, this particular positions are actually happening like it will be splitting on the top direction, on the bottom direction. So there occurs a splitting tensile or the bursting tensile stresses within the beam itself due to this anchorage plate. So we are basically concerned about this particular loading condition, this particular stress conditions where bursting tension or splitting crack happens at the center of this particular anchorage plate at that particular level due to this uneven distribution of compressive forces. All right, so in this video basically we when we say that we are going to find out the stresses due to anchorage in the anchorage zone and then accordingly design, basically we are going to find out the bursting tension or tensile stresses that are developing, and against that we need to design our beam. Now, how do we find this bursting tension or the tensile stress distribution? How do we find these stresses? So, there has been many studies, mostly it's related to empirical formulas or formulas that has been generated in laboratory experiments. So one of the popular one is Guon's method. So here basically what we do is we have a depth of anchorage plate YP0. We have the depth of section. All right. So based on that, uh, we simply find bursting tension if my forces are evenly distributed. Like if the center of the anchorage plate lies at the neutral axis of the span, in that case I'm going to apply this particular expression to find the bursting tension. If it's not evenly distributed, then obviously in that case there are certain empirical formulas that has been provided through these tables. Okay, so these are mainly empirical formulas. If you need to know in detail how this is coming, you need to go through research articles and papers. If you need that, you can DM me. I'll be happy to share it with you. Okay. Now these are the tables like I discussed. You need these particular values. These are the obtained from experimental results. So if you simply we go to a problem, let's see how we can is very easily solve it using Guon's method. So in this problem, it has been referred to a previous problem, but I'll just the required data simply is written here. You have a pre-stressing force of 100 kilonewton. You have an anchorage plate depth of 250 millimeter, and total depth of the section is 200 millimeter. So you need to calculate the distribution ratio. Like see in this case, the distribution ratio is given as YPO divided by YO. So, based on the distribution ratio and from table 10.2, that is this one. So, if based on this distribution ratio, you can find the position of the zero stress, where at which point the stress is equals to zero. You can find the position of maximum stress, and obviously you can find the ratio of maximum tensile stress to average stress. So accordingly, position of zero stress has been calculated for this particular yp not divided by yo, and then position of maximum stress. From there, maximum tensile stress has been calculated, which is found to be 0.345. This 0.345, again it's taken from the that particular table. 0.345 p by a. P by is a is the average stress. So you get your maximum tensile stress. All right. So this is how you calculate, basically. Uh, Simply, bursting tension is calculated FPST. The expression that you have here, bursting tension, has been calculated using this expression. Simply like this way, like if you have a yield stress of mild steel, 260 Newton per millimeter square, area of steel required to resist that particular tension has been calculated to be 73 millimeter force by stress. All right. So there you have it. This is a very simple method using Guon's method. I'm not going into much detail in this method, because this method is not actually referred or recommended by IS 1343. Right? It's not the not given in IS 1343. So what is actually given is the Zielinski and Rose method. This method is basically recommended in many of the standardized codes. Again, you have a diagram here which actually shows the mechanics of this uh, expression or the problem. I'll just sum it up to you. The expressions are, the recommended equations are basically tensile force is calculated equals is as per this expression, where valid it is valid for a ratio of the distribution ratio of equals to 0.3 to 0.7. Then you have a bursting tension calculated as per this expression, right? Now, if there is allowance made for tension taken by concrete, like if you in the problem you want to uh, say you want to assume that your concrete can take some amount of tension, since we are using pre-stressed concrete, we are expected to use high grade of concrete, so you may assume certain allowable limit for tensile stresses in concrete. In that case, you need to incorporate that here. Ft, that is given as permissible tensile stress in concrete. So this will be your corrected value of bursting tension. All right. One more new important information is, as per this method, you need to provide reinforcement to resist the bursting tension between 0.2 y0 and 2 y0, where the intensity of the stress is maximum. So this is your range where you provide the uh, reinforcement to resist the tensile stresses. Okay. So again, you have a, example. Let's quickly get through this. Uh, Again, the same example that has been used before. So we basically need the data here. So again, like we have a pre-stressing force of 100 kilonewton. We have a depth of the anchorage plate equals to 50 millimeter. We have total depth of the section as 100 millimeter, and the distribution ratio here is taken as 50 by 100, obviously. So 0.5. So here FC is basically you're having so allow me to correct myself. Uh, just one small thing that has changed in case of this method is, this method is based on assumption of a prism. So like if you have this unshaded portion as anchorage plate, right? This unshaded portion here as anchorage plate. Here the shaded portion, which is basically another extended square of that particular anchorage plate, this shaded portion is called the prism of the anchorage plate. So unlike the previous method where we had a total depth used as 2y0, in this case we are going to use the dimension of this particular extended prism as 2y0. So if you are having like a depth of anchorage plate is equals to 50 and width also 50, again it can go as max to as this direction, like extended direction. So in this case obviously if you have 50 millimeter of dimension of anchorage plate, square anchorage plate, maximum possible in this case would be 100 millimeter. All right. So, so since FC is basically the average stress that has been calculated, average stress present in the prism, like if you see here, average compressive stress in the prism. So FC is calculated using that. So then you have the calculation of tensile stresses that is present as per this expression, and then again you have bursting tension expression as per this one. And if you are going to assume an allowable tensile strength capacity of the concrete, you are going to using this expression where if in this case it is assumed that concrete can take 2 newton per millimeter square tensile stress, so accordingly it has been put and corrected value has been put here. So this is how you calculate the stresses in anchorage zone, mostly bursting tension and tensile stresses. So this is another example. You try it at home. Okay, so it's pretty simple. So give it a try once. Now I'm going to straight into the recommendation of IS code. All right. Now as I mentioned earlier, uh, IS 1343, that is the IS code for pre-stressed concrete design according to that. In calculation of anchorage stresses and designing, it follows the Zelinsky and Rose method here as well. So you have a bursting tension expression which is similar to the expression given by Zelinsky and Rowe, where Pk is given as the tension jacking force, or we can say the pre-stressing force that has been applied, and obviously YPO and YO is the distribution ratio. All right. Uh, one few more things. Uh, like distribution of this reinforcement is provided in the zone of zero point 0.2y to 2y from the loaded phase of the end block. So whatever reinforcement we will be providing will be provided within that particular zone, and the bursting tension is present and it is assumed to act at its design strength of 0.87 fy, which is usually the cases are. Now these are some arrangements of reinforcement in the end block. Uh, Usually it is provided in shapes like this to resist the bursting tension. Mostly the tension is uh, in the vertical direction or the transverse direction, not in the longitudinal direction. So it is the reinforcement is provided according to that. Now there is a possibility that even if you provide the reinforcements where bursting tension or in which particular direction bursting tension is developing, but you may ignore some part like this top portions or the bottom portion or the corner portions are mostly susceptible to spalling. So if you simply provide uh, reinforcement within the member to resist the anchorage stresses, obviously this particular shaded portions are going to fail. So the correct way to do is basically provide a caging system to the pre-stressed member at least around the corners to avoid the spalling portion. Now we are coming to a very simple example. We have a problem of a pre-stressed member where we need to provide anchorage reinforcement as per Indian standard code. All right. So in this case, let me read through the problem. The end block of a prestressed concrete girder is 200 millimeter by 300 millimeter deep. The beam is post tensioned by two Fresnel anchorages, each of 100 millimeter diameter, with their centers located at 75 millimeter from the top and bottom of the beam. So we have a anchorage plate which is in shape of a circle, all right, and the diameter is provided to be 100 millimeter. It is located at 75 millimeter from the top and from the bottom. So we have the anchorage plate installs two anchorage plates installed at top and bottom, and the distance from top and bottom is 75 millimeter, and the total depth of the section is 150, 300 millimeter, and the two parts, top and bottom part, 150 150. Now the force transmitted by each anchorage is 2000 kilonewton. Compute the bursting force and design suitable reinforcements according to the Indian Standard Code. Alright, let's see how we can solve this. The anchorage diameter is provided to be 100 millimeters. So since usually what we do, we assume the anchorage plate to be square one. So in this case as well, since it's a circular one, in this case we have to assume a imaginary uh, anchorage plate which is of square shape and has same area as of the square. So that's how you have equivalent side of the square. Like we have to calculate the equivalent side. So it's coming out to be 89 millimeter. So a square having dimension of 89 millimeter will be will be having equal area as to a anchorage plate, circular anchorage plate having diameter of 100 millimeter. Now, obviously, as according to the dimension, side of the surrounding prison would be 150 millimeter. Since my if you extend this particular equivalent side of the square, so accordingly we calculate the distribution ratio to be 0.593. All right. Now the expression as given in IS code, if you apply it, we find out to be bursting tensile stress of uh, 286 kilonewton. Now we are using 10 millimeter diameter of mild steel link with yield stress of 260 Newton millimeter square. So number of bars required, you simply apply this particular formula which you have used countless times while calculating like spacing and all in case of design of RC structure. So 286 is basically your bursting tensile force, right? 1000 is like 1000 is like kilonewton, converting kilonewton to newton, and then 0.87 Fy, and 79 is your uh, I think area of the 10 millimeter diameter links. So as per that, you have number of bars required is to be 16. Now these bars are to be arranged in a zone of zero point 0.2 YO and YO. So within this particular zone, you need to provide this particular bars. So if you calculate the values, it comes out to be 15 millimeter to 75 millimeter. So you have to distribute this per number of bars, 16 number of bars within this particular span. So let's look at the diagram here. So this is basically your arrangement. These two are the anchorage plates, circular anchorage plates that is provided, and it is located from bottom 75, from top 75, and this is the way the links are provided in this case. So these circular ones are the 10 millimeter dia links in Y and Z direction. 16 in each direction has been provided to resist the bursting tension. So there you have it, a very simple and short example how you can resist the anchorage stresses in case in prestressed post tension members as per IS 1343.